Welcome to the podcast, Stories from the World of Science. Our mission is to explain science in a simple and fun form that is open to all.
All right, ever try to picture a state so cold that, everything just stops?
Everything.
Yeah, and I don't just mean frozen solid. I mean, on an atomic level, even the atoms are barely moving.
You're talking about absolute zero.
Exactly. We're diving into absolute zero today, the ultimate bottom of the thermometer. And get this, we're using Sacha Deleng's article, Conquering Absolute Zero, to guide us.
Sounds like a chilling read.
Right. And what's really wild is that this whole quest started back in the late 1800s. Around the same time, explorers were racing to the North and South poles.
So like a different kind of exploration.
Totally. Except these pioneers were after a different kind of the most extreme cold imaginable.
It is kind of a mind-blowing concept when you think about it, trying to reach a temperature where theoretically everything just stops.
Absolutely. And one of the big names in this whole pursuit was James Dewar.
Dewar.
Didn't he?
Invent the thermos. Yeah, you got it.
Wow, I never knew that. So the quest for absolute zero led to keeping our coffee warm.
It's a funny twist, isn't it? But Dewar's work was about way more than just a hot cup of joe on the go. He was obsessed with liquefying gases, especially hydrogen, which has this crazy low critical temperature.
Okay, so maybe a quick refresher for our listeners who might not be up on their thermodynamics. What exactly are we talking about with critical temperature?
It's like, think about water boiling, right?
It's to steam.
Right. That happens because the water heats up past its critical temperature and it can't stay liquid anymore. Liquefying gas is like doing that in reverse. You got to make them so cold they switch from a gas to a liquid. And some gases, especially hydrogen, really don't want to make that switch. So Dewar's trying to wrangle these gases into their liquid form, and hydrogen's putting up a fight.
Basically. And it wasn't exactly a walk in the park. I mean, the article talks about explosions in his lab, insane pressure, even an assistant losing an eye because of the experiments. Talk about dedication.
Ouch. Yeah, that's commitment. So how do you finally crack the hydrogen puzzle?
Well, that's where another brilliant mind comes in. Johannes Dieterich van der Waals.
Van der Waals, what did he do?
He was the one who figured out that those forces between atoms and molecules, they actually affect how easy it is to liquefy a gas. It was like he gave Dewar the instruction manual he needed.
So thanks to Van der Waals, Dewar finally reached his goal.
He did. In 1898, he successfully liquefied hydrogen and hit a mind-blowing negative 250 degrees Celsius. But just when he thought he'd conquered the coldest substance, a new contender entered the ring: helium.
Helium. Even colder.
You bet. Turns out, helium was the key to getting even closer to absolute zero, pushing the limits of what anyone thought was possible. It's like he climbed Mount Everest, planted his flag, and then looked up to see K2 looming even higher.
Huh. That's a good way to put it.
Yeah.
So who took on helium then? Who was up for that challenge?
That would be a Dutch physicist by the name of Heike Kamerlingh-Onnes. And get this, Doling writes about how Onnes's wife had to spoon-feed him during the experiment because he was so focused he wouldn't even leave the lab to eat.
Now that's dedication. Some people get hangry, others get, laser focused on absolute zero.
Right, and all that focus paid off. In 1908, Kamerlingh-Onnes successfully liquefied helium.
Wow, and how cold did he get?
Then added at 269 degrees Celsius, just a hair above absolute zero.
Incredible. Yeah. So what happens then? Did everyone just pack up and call it a day? Okay, we basically hit absolute zero. Good job, everyone.
Not quite. See, reaching these crazy low temperatures wasn't just about, checking off a box. It was about unlocking the secrets of matter at its most fundamental level.
Right, because things get weird at those temperatures, don't they?
Weird is an understatement. With liquid helium, they could finally see what happens to matter at the edge of absolute zero, and what they found was truly revolutionary.
Okay, got to give me an example. What kind of weirdness are we talking about?
Imagine a world where electricity flows with absolutely zero resistance.
Zero resistance. What, like super efficient power grids? Phones that never die?
Exactly. That's superconductivity, and Kamerlingh-Onnes stumbled upon it while messing around with supercooled mercury.
So you're saying if we could just make everything as cold as liquid helium.
We could have some pretty mind-blowing technology. Of course, keeping things that cold outside a lab is a whole other challenge, but the discovery of superconductivity was huge. It proved that near absolute zero, the rules of physics as we know them, they kind of go out the window.
Wow, okay. So we've got superconductivity. What other weirdness did they find?
Well, there was this thing called superfluidity.
Superfluidity, that sounds kind of ominous.
It's actually even weirder than it sounds. Picture this. You've got liquid helium, and you cool it down even further than before. Suddenly, it loses all viscosity.
It's like, what, it flows without any friction.
Exactly. It defies gravity, even climbs up the walls of its container. It's like it enters a completely different state of matter.
That just sounds like showing off, honestly. How can something even do that?
It's all thanks to the wacky world of quantum mechanics, which basically means all bets are off when it comes to the normal rules of physics. And as it turns out, a young Indian physicist named Satyendra Nath Bose had an idea about this that would change everything. So we've got this young physicist, Satyendra Nath Bose, right at the edge of like a scientific revolution. What was this big idea that shook things up?
Okay, so Bose was looking at how we think about particles, specifically photons, those tiny bits of light.
Yeah, okay, I'm following.
His idea was kind of out there. He suggested that at super low temperatures, way down near absolute zero, particles could actually lose their individual identity.
Lose their identities. What does that even mean? Do they forget who they are?
Not exactly. It's more like, imagine a room full of people, each with their own voice, right? But then you crank the AC down to near absolute zero, and suddenly all those voices blend into one. They become like a single unified wave instead of a bunch of separate particles.
So instead of bouncing around like individual ping pong balls, they all kind of blur together.
Exactly. They could become this single quantum state. It's like they merge into a single superatom.
Wild. So this was a pretty radical concept back then.
Oh, yeah. The scientific community wasn't quite ready to rewrite the rules of physics. In fact, Bose's paper was actually rejected by a few journals at first.
Ouch. Rejected. So how did his idea go from being dismissed to like changing how we understand the universe?
Well, Bose, he had a pretty good backup plan. He sent his work to, well, who else? Albert Einstein.
Einstein. Talk about a Hail Mary.
Right. And thankfully, Einstein, he saw the genius in Bose's work, called it a significant advance.
That's like getting a standing ovation from the smartest person in the room.
Exactly. And Einstein didn't just stop at a pat on the back. He actually worked with Bose to develop the theory even further.
Wow, what a team. So what came of this amazing collaboration?
Well, they predicted that this new state of matter, this superatom, it could actually exist. And they called it a Bose-Einstein Condensate, or BEC for short.
A BEC. So did they ever actually make one?
Not right away. It took almost 70 years, a whole lot of technological leaps and bounds, but in 1995, researchers did it.
They created a BEC. Wow. What was the recipe? How do you make something that's basically colder than space?
It was intense. They used lasers and magnetic traps to cool down this cloud of rubidium atoms. And, I mean, they got it cold, like a fraction of a degree above absolute zero.
It worked.
It did. The BEC formed, just like Bose and Einstein predicted, this group of atoms acting like one single entity, all in sync.
That's incredible. And you said this new kind of matter, it doesn't even exist naturally, not even out in the vastness of space.
Nope. Even the coldest corners of space are still not cold enough for a BEC to just hang out. This was something totally new to the universe made right here on Earth.
We started with exploding labs and ended up creating matter colder than the universe itself. That's mind-blowing.
It really makes you wonder what other secrets are hiding out there in the extremes,
Yeah.
The super hot, the super cold. Who knows what we'll discover if we keep pushing those boundaries.
It's a bit humbling, isn't it, knowing there's so much we haven't even begun to explore?
It really is. It's a universe full of mysteries, and sometimes it takes venturing into the most extreme conditions to even catch a glimpse of them.
Well, on that note, I want to thank you and all of our listeners for joining us on this deep dive into absolute zero. It's been quite the adventure. If you're as blown away by these discoveries as we are, head over to social media and let us know what surprised you the most using #TheDeepDive. Until next time, stay curious.
You just listened to the podcast, Stories from the World of Science, written by Sasho Dolines.